we knew what our initial deposit was, and we wanted to see what's going to be our ending balance. Now we're going to take a look at, okay, I want my ending balance to be this. How much do I need to deposit now? Okay, so that's what the whole notion of present value is about. So in looking for the future, the problem often arises: how much money P should be deposited now at a fixed rate in order to have a balance of A after T amount of years, T amount of years from now. So we call this question is given by the present value of A. So to find the present value, we take our original function, A equals your initial deposit times 1 plus your rate over N to the power of NT, and then we just solve for P. So we just divide both sides by this part here, and so you get that P is A over this, or the amount you need to deposit now can be defined as A over 1 plus I to the power of N, where your I is your percentage rate divided by your number of compounds per year. This is going to be the interest rate per compounding period. Again, rate per compounding period. That's why it's R divided by N. And then big N is going to be N times T is the total number of compoundings per year. Say you compounded 4 times for 1 year, or 4 times a year for 5 years. So that would be 4 times 5. So that's where this NT comes from. So you can use the one on the left or the one on the right, depending on how the question is presented. So let's look at example 3, finding present value. So we have an investor is purchasing a 12-year certificate of deposit that pays an annual percentage rate of 8%. It's compounded monthly. How much should the person invest in order to obtain a balance of $15,000 at maturity? Okay. So let's see. An investor is purchasing a 12-year certificate. So if it's 12 years, that means your T is 12. If the annual percentage rate is 8%, so then your rate is 8%. If it's compounded monthly, there are 12 months in a year, so your N is 12. How much should the person invest so that the ending balance or the amount at the end is 15,000? So our A is 15,000. So then once we know all of these notions, we just plug the values into our formula for present day value. So if we want $15,000 at a rate of 8% compounded monthly for 12 years, then we need to deposit $5,761.72 today, so that 12 years from now, with these given rates compounded monthly, we'll have the $15,000. Okay. So the person should invest $5,761.72 in the certificate of deposit. Okay. Deposit that today with these given conditions, you'll have your $15,000 12 years from now. Okay. So I'm going to end the discussion there, and we'll pick up on the next video lecture to close out section 4.3. All right, this is section 4.3, derivatives of exponential functions. So again, in section 4.2, we stated that the most convenient base for exponentials is our irrational number e. The convenience comes from the fact that the function f of x equals e to the power of x is its own derivative. So we chose that irrational number because f prime, if your f of x is e to the x, and your f prime is also going to be e to the x. This is not true for exponential functions of the form y equals a to the power of x, where your a is not equal to e. So now, again, we defined e to be the limit as our delta x goes to 0 of 1 plus delta x to the power of 1 over delta x. This is our definition for e. When you see something of this form, then you think e. So now this says that as delta x approaches 0, or in other words, for really, really small values of delta x, e is approximately this 1 plus delta x to the power of 1 over delta x. Again, e is approximately 1 plus delta x to the power of 1 over delta x. But then if this is e's approximation, then e to the power of delta x is going to be approximately 1 plus delta x. Because here, if you have a power of 1 over delta x to the power of delta x, then the exponents cancel and that exponent becomes a 1. You have 1 over delta x times delta x, and it becomes just a 1. So the power of this becomes a 1. If you think about it, just take your e and then raise it to the power of delta x, you'll get this. So take this definition to the power of delta x, you get this. Okay. So now we're going to use this result, that e to the delta x being 1 plus delta x. We're going to use this in the result to show, okay, even if you apply it to the limit definition of derivative, remember that limit as delta x went to 0 of your change in y over change in x, you can show that e is its own derivative. So say you start with f of x equals e to the x. So then our limit definition of derivative, our f prime, is going to be the limit as delta x goes to 0, your change in y over change in x, your y2 minus y1 over your x2 minus x1. Okay. Again, this was just our definition of derivative. So now, if our f of x is e to the x, so then this is going to be e to our new x minus e to the x, e to the x. Okay. Notice both of these have e to the x that can be factored out. So then you're left with e to the x times e to the delta x minus 1. But we just showed you that e to the delta x is 1 plus delta x. So then this part here becomes 1 plus delta x minus 1. That just leaves you with the delta x. The delta x is canceled. Now you're just left with the limit as delta x goes to 0 of e to the x. But then, so now notice there is no delta x now. So this limit as delta x goes to 0 is just e to the x. Okay. So again, we like to do a lot of discussion on exponentials using the base e, because f of x equals e to the x is its own derivative. In other words, your e to the x is its own derivative. Okay. So now, if u is a function of x, we can apply the chain rule to obtain the derivative of e to the u. So the derivative of the natural exponential function. Let's see. Let u be a differential function of x. So for part 1, the derivative of e to the x with respect to x is just going to be e to the x. And then for part 2, the derivative of e to some f of x, because again, u is a differentiable function of x. So the derivative of some e to f of x with respect to x is going to be e f of x times f prime. In other words, our d by dx of e to the u is going to be e to the u times u prime. Du by dx is nothing but u prime. So in the second part, we use the chain rule. So derivative of e to the x is just e to the x times x prime. It's just the chain rule. Okay.